Today, we're going to dig into literally one of the most fundamental tests in all of civil engineering. It's something that happens long before you ever see a steel beam go up. We're talking about the standard penetration test, a surprisingly simple but incredibly powerful way we learn to read the ground right under our feet.
So, just imagine for a second. You've got the plans for a massive new skyscraper. You know everything about what you're building up. But what about what's happening down?
Because really, the biggest mystery, the biggest risk, is right below the surface. Before a single shovel of dirt is moved, you have to answer the most important question of all. Can the ground actually hold up this massive thing you're about to build? And that brings us right to our first section, the groundwork question. You should think of this whole process like a detective story. The mystery is buried deep in the soil, and the engineers, well, they're the investigators trying to crack the case.
Here's the challenge. You just can't look at the surface and know what you're dealing with. Every single patch of ground is unique. Is it dense, strong sand that can take a huge load? Or is it soft, squishy clay that could mean absolute disaster down the road? Building on the wrong stuff isn't just a bad idea. It's a recipe for catastrophic failure. And that is exactly where the standard penetration test, or SPT for short, comes into the picture. It was developed in the United States way back in the 1920s, and for 100 years it's been the go-to method. It's simple, it's low cost, and it gives engineers a first look at the soil, right there on the job site.
Okay, so how does this century-old test actually work? Let's get into the nuts and bolts in Section 2, the hammer drop test.
You know, the process is almost brilliantly simple. First, a drill rig bores a hole down to whatever depth they need to test. Then, they lower in this special hollow tube called a sampler. And then comes the main event. A 140-pound hammer is dropped over and over again from the same height, driving that sampler into the soil. All the while, the crew is on the ground, carefully counting every single blow. Now, they count the hammer blows for 3 separate 6-inch sections. But here's the interesting part. They throw out the count from that first section. That's just to get the sampler settled in the dirt. What they really care about is the N-value, and that's the total number of blows it takes to drive the sampler the last 2 sections, so the final 12 inches. This N-value is the raw clue, the first piece of data they get from the field. But here's the thing. That raw number, the N-value, it's not the whole story. In fact, if you just use it as is, it can be really misleading. And that takes us to our next section, standardizing the score. So let me ask you a question. If you get an N-value of 10 on a site in Japan, is that the same as getting an N-value of 10 on a site in the United States? I mean, it seems like it should be, right? But the answer is almost definitely not. And this table shows you exactly why. The equipment people use around the world just isn't the same. Take a look at the hammer efficiency. In Japan, they often use a free fall hammer that delivers about 78% of its energy. But a common rope and pulley system in the US might only transfer 45% of its energy. That is a massive difference. You could have the exact same soil but get totally different N values just because of the rig you're using. So, to make it a fair fight, engineers have to correct that raw N value. They adjust it for all sorts of things, like the hammer energy, how long the drill rod is, and a few other factors. The goal is to standardize the result as if the equipment always delivered exactly 60% of its energy. This corrected, standardized value is called N60, and that's the number that lets you compare apples to apples anywhere in the world.
Okay, so we've done the test, we've done the corrections, and now we have our standardized N60 value. So what? What secrets does this one little number actually tell us about the ground?
Well, the really crucial thing to understand is that N60 isn't the final answer itself. It's the key. You see, over decades and decades, engineers have built up this huge library of charts and formulas that connect the N60 value to the real-world properties of the soil. It's like a Rosetta Stone for dirt.
For instance, if you're in sandy soil, a higher N60 value is generally a good sign. It means the soil is stronger. Engineers can use it to estimate the relative density. Basically, is the sand loose and fluffy, or is it packed down nice and dense? They can get an idea of the soil friction angle, which tells you how well the sand grains lock together. They can even figure out how stiff the soil is. And it's just as useful for clay soils. Just look at this table. The N60 value correlates directly to the clay's consistency. If you get an N60 less than 2, you're dealing with very soft clay, not something you want holding up your building. But if you get a value over 30, that tells you the clay is hard and very strong. This is absolutely critical information for designing a foundation. But for all its power, it's really important to understand where the SPT fits in. It's not magic. And that brings us to our final section, a tool, not a rule. Look, the SPT is popular for some very good reasons. It's simple, it's cheap, and engineers all over the world know how to use it. Plus, and this is a huge bonus, you get an actual physical sample of the soil to look at. But, and this is a big but, it has major drawbacks. The results can be all over the place, and they really depend on the specific equipment and, maybe most importantly, the skill of the person running the test. It's just not a high-precision instrument. This quote from a geotechnical expert, Bengt Felinius, really hits the nail on the head. He says that just blindly plugging the N-value into a formula is, quote, unsafe and imprudent. The number only has real meaning when it's interpreted by an experienced engineer who knows the local geology. It's where the science of testing meets the art of engineering judgment. So the next time you're walking by a construction site and you see one of those drill rigs hammering away, you'll know exactly what they're doing. They're asking the ground to give up its secrets, one hammer blow at a time. And now you can ask yourself, what kind of secrets do you think they're uncovering?